Hello again. We are currently in the middle of the proof of the Rees-representation theorem. The Rees-representation theorem is a result that allows you to characterize all linear functionals on a Hilbert space. Okay, the statement is here again. We have so far, done some initial steps in the proof. The idea is to start with the kernel, which is a closed subspace. Then there's a trivial case if the kernel is already everything, meaning S is equal, the kernel is equal to the Hilbert space, then you're done because the functional maps everything to 0. If that doesn't happen, then you know by a previous result that you have a non-zero vector in the orthogonal complement of that kernel. You define auxiliary quantity y, which is just a multiple, and then you check a few things. First off, if you now evaluate again on the kernel, then the inner product xy with that particular element y is equal to 0. Okay, so you have this representation established if you are in S. Now, if you are now looking at multiples of the non-zero vector in the orthogonal complement, then you also have the same equality. Fx is equal to xy. That requires a little bit of a computation in between. Now, having that established, what is now the punchline? In summary, of these two steps, of these two green underlined equality, in summary, the maps x, f of x, which is just a linear functional, and this one, which sends a given vector x to inner product x with this constructed quantity y. They are both linear. And they agree on, well, these were the two green underlined things. On the previous one, the first green underlined thing was that they agree on S. And, well, they agree on, well, when x is alpha x naught, well, that's precisely the span of x naught, right? All possible linear combinations that you can form out of this one vector, which are just the multiples of this vector. So, and span x naught, all right? But now we use the projection lemma again. So far we have only used it in the form of this corollary that the orthogonal complement of a proper closed subspace has more than the zero vector in it, but now we're going to use it in full generality. But since for all x in H you have the following representation, so x is, so let's write here something, f of x naught and x naught. By the way, here this is well defined because the denominator f of x 0 is different from 0, and that's because of, well, of the projection lemma, because x naught is in the orthogonal complement of the kernel, so it's not going to be mapped to 0, right? This will only happen if you are in S, but not if you're in the orthogonal complement. That's the projection lemma there. And then, well, it's not an equality yet, but now it will be f of x naught times x naught. So you can see that this is an equality, that ratio just goes out. But now what happens here is this one here, this is a multiple of x naught. So this is in the span of x naught. And what is this here? Well, hopefully it's in S, right? In the kernel, and it is, right? So if you put here, I will write down in S, since, well, you just use the linearity. So f of x naught, x naught, to use the linearity, it is f of x. This is a scalar, so f of x naught, and then f of x naught, and this is precisely equal to 0 because these two guys, they go out. Okay, so you can, any vector in the Hilbert space you can represent as the sum of something in S written out there and something in the span of x naught. Yeah, but you already know that f of x is equal to inner product xy on both of those. So immediately now by this decomposition, you know f of x and xy are equal to one another on the whole space, right? By linearity. Okay. So we obtain from this, but since for all this we have f of x is xy for all x in H. Okay, that's the first thing. Now we have to establish uniqueness, and then we have to establish the equality in norms between vector y and the operator norm of f. Okay, so let's do this for uniqueness. In order to establish uniqueness, we assume that, well, I can represent f in this way for some y, but also in this way for some, say, y prime. Okay, and now of course the idea is to show that y is equal to y prime. Yeah, but then it's easy enough computation. So y prime minus y in norm squared. Remember the norm in a Hilbert space, that's the induced norm. So it is equal to this. All right, and then you use the properties of the norm. You can write this as y prime minus y prime minus y prime minus y. Okay, you just, split here. All right, but now look, you have, let's use two colors. You have this representation and you have this representation. In the first one, I'm going to use the green one. So this is equal to f, and now it's not x in the first vector, but y prime minus y. So here I use green. And then in the second one, I'm going to use red. Again, the vector is not x in the first entry, but y prime minus y here. Yeah, but now you're subtracting the same quantity right, from each other. So that is obviously equal to 0. That is equal to 0. And you have shown that a norm is equal to 0, and that only happens when the vector inside is the 0 vector, and here this just means that y prime is equal to y. So you have uniqueness of the representation. So y prime is equal to y, it has uniqueness. Follows. Okay, last thing that remains is the equality of norms in order to prove y, the norm of y is equal to the operator norm of f. We observe that, so earlier I wrote in the other video, the one before this one, I wrote the definition of the operator norm. That's the supremum of a non-zero vectors and then that ratio. Equivalently, you can take the supremum over vectors that have length 1. Right? I explained why this is the case when we first introduced the operator norm. So you have this. Yeah, but now you have, of course, the representation formula, which we already established, which is that f of x is just the inner product x with y, and y is that quantity that we actually constructed explicitly in the theorem. Okay. So yeah, but now, of course, we use Cauchy-Schwarz for the inner product, which we proved in a previous video as a consequence of the Bessel inequality. So you have x is, let's use a bracket here, x, y. Yeah, but then of course this here, this quantity is completely independent of x, and the supremum of the norm of x when the norm of x is equal to 1 is 1, right? So this is equal to norm of y. So you have one inequality, right? This here is at most equal to that one. Now you have to show the reversed inequality and then you will be done. Okay, let's do this on the next page. Moreover, we have f is same formula, supremum x in the norm is equal to 1 of f of x. And now I'm just gonna, well, evaluate f on that vector y. Okay, yes, like this. So this one here, since it is a vector of length 1, this one here is at most equal to the supremum, of course only in complex modulus or absolute value. Okay, so this is true. And now you just use the representation formula again. So this is equal to y, comma, well, the same y, okay? Yeah, but this here is what? Well, this is the norm of y, right? Because you pull out the scalar factor, that one you can pull all the way out, and then you have the inner product y with itself, which is the norm squared, okay? And that's why you can divide out one power and you go out here with power 1, right? And this is the other inequality. By the way, here of course you can say, okay, what happens when y is equal to 0, because then I can't divide. But remember, when y is equal to 0, that precisely happened when the functional maps everything to 0, right? And when the function maps everything to 0, its operator norm is obviously 0, and then this inequality is still true, right? 0 on the left and 0 on the right. So that it all works out. Okay, and that's it. That's the proof. All right, so this is Riesz representation. It's remarkable. The proof is fairly simple, using the projection lemma that is crucial input, and then constructing this vector y. Okay, nice. We will leave it at that. We will use it again heavily in chapter 3. For now, just take it as a fact that any linear functional is of this, well, is an inner product. That's what it says. Okay. On a Hilbert space. Any linear function on a Hilbert space is an inner product. Good. Now, the next section. So this will be section 2.3. I can build a nice bridge to that. So it will be about orthonormal basis. So in ordinary linear algebra, when everything is finite dimensional, the notion of a basis is well, crucial. I would say almost everything, you know, in linear algebra is proven by expanding vectors in some basis. In particular, if you discuss Riesz representation, of course this proof now also works in finite dimensions, of course, but if you usually prove Riesz representation in linear algebra, you also use a basis. You start with a basis of the inner product space, and then you have the dual basis, and that's how you cook up, you know, that vector y. Now here we're going to do similar things. So we want to make sense of, well, what is a basis in infinite dimensional vector space, okay? So we will have, by the end of this section, we will have a way of representing vectors in a Hilbert space as certain linear combinations of, well, whatever these basis vectors are gonna be, okay? That's more or less the idea. The big difference to linear algebra is now the way how we will prove that bases exist is highly non-constructive. So in linear algebra, you can do this sort of by hand. You add one vector at a time in a way that it's, you know, linearly independent to the ones that you already have. And then at some point, because the space is sort of, you know, finite dimensional, the process terminates. So you go one vector at a time. But here that is, you know, bound to fail, because we will see that we will have bases with uncountably many elements in it. So we need a completely different tool, and that is a highly non-constructive tool. This is Zorn's lemma. So Zorn's lemma, which we will discuss in the next video extensively, is a sort of, well, a kind of mathematical induction tool that helps you to get a grasp on uncountably large sets in a sense. Okay, we will use Zorn's lemma many times actually. Here now in the section on orthonormal basis, it's the first time. Okay, but let's first make sense of what is a basis, an orthonormal basis. So I can't write now here, you know, things in terms of spanning sets, because, you know, these sums, they might have uncountably many terms. So how do we define this? Well, we have to be a bit clever about it. So we know what orthonormal sets are. And if S is an orthonormal set in a Hilbert space H, and no other orthonormal set contains S as a proper subset, contains S as a proper subset, then S is called a complete orthonormal system or an orthonormal basis. Okay, for H. All right, so an orthonormal set in a Hilbert space, and no other orthonormal set, sort of a bigger one, contains S as a proper subset, then S is called a complete orthonormal system or an orthonormal basis. So here, just word of warning, this complete here, this has nothing to do with Cauchy sequences. We are in a Hilbert space, so Cauchy sequences are convergent, our space is complete. That word complete here has a different meaning, okay? I think I mostly use actually the phrase complete orthonormal system instead of orthonormal basis, but of course you can do as you please. But why do we use complete orthonormal system here? So here's a comment. So any complete, in what sense is it complete? Any complete orthonormal system S, so that guy, now we will use again the index sets that can have uncountably many elements in there. It can be finite, can be countably infinite, or can also be uncountable. In H has the property that if X is in H and X alpha is equal to 0 for all alpha and I, then this implies X is equal to the 0 vector. So that is an important characterization of complete orthonormal sets. And by the way, any orthonormal system that has this characterization, which satisfies the yellow box, is a complete orthonormal system. Oh, I wrote orthonormal twice. Any complete orthonormal system. Okay. Why is this true? Well, this is because of how it's defined up there. So because if X, let me write it in maybe, pink, if X alpha is equal to 0 for all alpha and I, and X would be different from 0, then this one here would be a orthonormal system that contains S properly, right? And that is, of course, a contradiction to the definition, because the orthonormal system is complete from the get-go, okay? So it is in this sense that the orthonormal system is complete. You can't adjoin yet other elements to it. That's why I said earlier, you can't make it bigger, okay? It's sort of already the biggest that there is, okay? That's what we mean by the completeness. So if X is a vector, an arbitrary vector, that is orthogonal to everything in the system, that in the orthonormal system that you start with, then if the system is complete, the vector has to be 0, and that's also a two-way route. So if this yellow box is satisfied for an orthonormal system S, then that system has to be complete. Okay, and here in pink is the reason why. Because if that X were not equal to 0, then you could enlarge S by that one vector, by at least that one vector, and then you would have something that contains S properly, and that you can't have. Okay, good. Now, the big theorem about, well, these orthonormal systems. So this is, well, the existence theorem. Okay, but the proof is highly non-constructive. So a Hilbert space H, it shouldn't be trivial. So there should be at least one non-zero vector in there. Having a non-zero vector has at least one complete orthonormal system. Okay, moreover, it's also something that you know from linear algebra. If S is any orthonormal set in H, then there is a complete orthonormal system containing S as a subset. Okay, so maybe it's good to have a quick bridge to linear algebra. The equivalent of this theorem in linear algebra is, well, that any vector space has a basis, in the sense that this is a linearly independent spanning set. This is what you do in finite dimensions, okay? And the second part would be, if you start with a linearly independent set, then you can enlarge it gradually. That's what I talked about earlier, sort of add one vector at a time until you exhaust, you know, the whole space, and then you're done, okay? Now here, this is in a Hilbert space. That's the first big difference. So you need the inner product and you need the completeness. And now it says there is at least one complete orthonormal system, and if you start with any orthonormal set, then also in a sense you can enlarge it, you can lift it to a orthonormal basis for the space. Okay, that's the statement. Now, unfortunately, the proof, this is non-constructive. Okay, so I will write a few lines and then we will stop, because we need a tool, which is Zorn's lemma. So Zorn's lemma I summarized in the section 1.1 of the lecture notes. This has to do with relations and order relations. So before maybe you watch the next video, it's good to have a read ahead of Zorn's lemma, and in particular, you know, refresh knowledge about relations, equivalence relations, reflexive, transitive, symmetric, and so on and so forth. I will also do a review in the next video, but maybe as a homework assignment, do it already in advance. So how is this proof gonna work out? Well, we're gonna start with, let S be an orthonormal set in H, any orthonormal set. Now such a set surely exists because by assumption my vector space contains at least one non-zero vector, right? That's what's written there. So the easiest orthonormal set that you can construct is, by the way, the same that we used in the proof of Cauchy-Schwarz inequality. For instance, if X is, you know, that one non-zero vector, then this guy here, just taking S, X and normalizing it, that is an orthonormal set. Okay, so there's at least one orthonormal set. And now the idea is, well, to make that one big enough, so to say, to blow it up and then hopefully get a complete orthonormal system or a basis. So how are we going to do this? Now consider following set C, which is the set of all orthonormal sets in the Hilbert space. Consider S is an orthonormal set. So the set of all orthonormal sets. Okay. Now what you have to do is, let me write this out. So the collection of all orthonormal sets in H. Okay. Now what you have to do is you have to introduce an order on that collection Okay, as I said, you have to review what orders are. I will do it also at the beginning of the next video. But now, once you can introduce an order on that, and you can order these sets. So remember, on the real line, you have a natural order, right? One element is less than or equal than the other if something happens. You can do a similar order construction here on that set curly C, which is the set inclusion, right? And now, once you have that order, then there is Zone's lemma, which sort of allows you or guarantees existence of a certain maximally ordered set, and then what you check at the end is actually, yeah, that's your orthonormal basis. So that's kind of how it works. It's an abstract reasoning using Zone's lemma that guarantees existence of certain, you know, elements there which do what you want. Okay, so it's clearly abstract. As I said, I will review Zone's lemma at the beginning of the next video. It's good if you have a look ahead, because it's a different flavor type result. It is not something algebraic or analytic, something that you discuss in metric Banach spaces. It has to do with order relations. Okay, this I will do in the next video. We will prove this theorem, and then we will really, you know, operate with the basis. So as you had it in linear algebra, if once you have a basis, you can write vectors as linear combinations, and we will do similar things here in the Hilbert space. Okay, this will be the so-called Fourier expansions that we will prove, and then we will restrict our attention to some, you know, special Hilbert spaces, these so-called separable Hilbert spaces. So you know from a metric space module what a separable space is. That is has a countable dense subset. And if you are in a separable Hilbert space, not every Hilbert space is separable, then actually you can even make this proof here much more constructive, because then there is the Gram-Schmidt process that helps you. Okay, but for now, since we're not assuming separability here of our Hilbert spaces, we will have to invoke Zone's lemma and prove it that way next time. Okay, hopefully I will see you again in the next video.